I'm Nathan.
And I'm Aaron.
And we are coming to you straight from Bridger's basement.
The wonderland of science.
So this is physics, and today we are going to talk about something very interesting.
And what would that be, Nathan?
We are going to talk about kinematic equations and how it applies to tennis.
Ooh, that is titillating.
It is. Why would you choose that word?
It's a fun word.
Okay. Now, there are different things that we can apply to tennis. When I explain this, we're going to oversimplify everything for the sake of the video.
Oh, fun.
Let's talk about when you're serving. What do you do when you serve?
Toss the ball up in the air and you smack it with your racket.
That's about it. But what if you wanted to find out how far your ball went when you hit it to the other side?
Well, how could you possibly know that?
Well, it's very simple when you use kinematics.
Okay.
Let's say you want to find how far it was. You'd have to know how fast you hit it with your racket, and you'd have to know how long it takes from the moment it hits your racket to when it hits the ground.
Okay.
That is delta x equals vi delta t plus 1/2 a delta t squared.
Okay, so let me take a stab at this. Delta x would be the distance that the ball travels, yeah?
It's the displacement, the change in x.
Okay. Vi would be the speed at which the ball is launched from the racket.
Close. We don't want to mix up speed and velocity.
Okay.
They are different things.
Velocity at which the ball is launched from the racket. Delta t would be the time it takes for the ball to travel from the racket to the ground. And a would be the gravitational constant, which we all know to be negative 9.81 meters per second squared.
That would be your acceleration. So you can just find out how far it goes from using that equation. Plug in your numbers for your variables and find delta x. What about if you want to find out how fast your ball is traveling in midair? We can actually solve that sort of thing when you serve. Say you hit the net.
Okay.
It's traveling at the same velocity as it would if you didn't hit the net, right?
Yes.
Just given that, you'd use the equation Vf equals Vi plus a delta t.
Okay, so that would mean Vf would be the velocity at which the ball hits the net. Vi is the same as from when we were serving the ball. It's the velocity at which the ball leaves the racket. A is gravitational acceleration constant, and delta t is the time it takes for the ball to reach the net.
Yep, and when you plug in your numbers, you can actually find out what your final velocity is at that moment it hits the net.
Yeah, that's pretty cool.
Yeah. What do you sometimes do when you try to serve? I know you're not too skilled at tennis, so...
I am horrible at the sport. Every now and again when I try to serve, I completely whiff it and miss the ball entirely.
Well, have you ever wondered how fast the ball is traveling when it hits the ground?
Sure.
This is something that we call free fall motion. And free fall motion is when the ball drops from a point and then it ends at another point. The biggest and most important part of this is knowing what your initial velocity is and applying acceleration.
Okay, so what is your initial velocity?
The initial velocity that we'll use in this case is 0, because when you throw it up, you don't hit it on its way up, you hit it on its way down. So we can just calculate it from when it's at 0 meters per second.
So what kind of equation would we use to calculate this?
We would actually be using the same equation that we just talked about when you hit the net.
So it matters which direction the ball is traveling. Is it traveling straight down? But we can use the same equation to express both?
Yeah, you can apply it to different directions, situations, just as long as it meets the criteria that the equation requires.
So we'd still use Vf equals Vi plus a delta t.
That would be perfect. Now, on the occasion that you actually hit the ball in your serve,
joy.
and on the rarer occasion it actually makes it over the net,
Oh, I am hot today.
I would of course return it, because
Okay.
I'm amazing. There's a special kinematic equation called the range equation. Let's just pretend that the starting height of the ball and the ending height of the ball were the same. Again, this is oversimplifying everything. Given that the starting and ending height are the same, you can actually find the distance that you travel by using the equation delta x equals negative 2 vi squared times sine theta times cosine theta all over ay.
That's a long and complicated equation. What all does it mean?
Your vi is, of course, your initial velocity.
Okay.
Now, your theta is the angle from the horizontal to where you actually project it.
Because when I hit the ball, it doesn't go straight outward. It goes up a little bit. It'd be that angle.
And make sure your calculator is set to degrees. If you try to use radians, you're going to have a rad time. And, of course, your ay is any acceleration downwards.
That'll still be negative 9.81 meters per second
Yes,
squared, right?
because ay gives that it is a one-dimensional motion there, you would use your y-ay.
And if we know those values, we can always find the distance that the ball will travel horizontally.
But only if the starting and ending height are the same.
Okay.
Let's get into max height.
Okay, so what if I want to find the max height, but there are parts of some equations that I don't know, and I do know some. How do I solve that?
Well, the truth is, Aaron, in real life, you can't solve most problems with just one kinematic equation.
Okay.
Like I said here, we were oversimplifying things, so let's apply apply some real-life know-how to this. So if you want to find max height, you would have to use the equation delta y equals vi delta t plus 1/2 a delta t squared.
So we know what all those variables mean from before. They're the same thing.
They are exactly the same thing. Say I hit a ball with a racket. If we wanted to find initial velocity, we would first have to apply a different equation. You know that equation that we were talking about earlier with hitting the net and missing?
Yeah. Vf equals vi plus a delta t.
Exactly. At max height, what do you think the velocity is?
So I'm gonna guess 0.
0
meters per second.
Knowing that, we can plug that in for VF, and if we can calculate the time, then we already know acceleration. We can find initial velocity. Now, we can actually calculate the time by counting the number of frames between when I hit the ball and when it reaches its max height. We can actually calculate it to 2 decimal places. It's actually only 1.23 seconds with sig figs. We know the time, we know the acceleration, and if you actually plug everything in together, you actually get an initial velocity of a whopping 12.0663 meters per second. But with sig figs, that's just 12.1.
I understand why I miss the ball all the time.
Knowing what our initial velocity is, we can actually plug that one in to the equation. When you plug 12.1 in for VI, plug in a time of 1.23 seconds, and
Negative 9.81 meters per second squared on the y.
and we add everything together, we get our max height.
I want to estimate it about 8 meters.
Close, 7.42 meters. It's moving very fast at the beginning, and that's the only reason that it's going that high. Now, if I'd tried throwing it, I'd probably never be able to reach that kind of initial velocity.
Yeah. Well, tennis has some surprising numbers in it when you actually sit down and do the calculations.
I thought it was very interesting. Did you learn a lot today, Aaron?
I did learn quite a bit.
It was very fascinating.
We can try to convince the audience as much as we want that this was fascinating, but it's up to them, really.